So I have written some references here. I hope that you guys can all read it, but I promise to make the fonts bigger from now on. But I'll share these references anyway. So let me go over the references. So this is the basic paper of Tuft, which introduced the notion of the large N technique for QCD, and then there's a then there was another paper by Tuft showing how this large N techniques can be used for two-dimensional QCD, and then so this is not chronologically listed. These two I'm going to use for the qualitative introduction to the subject, how large N counting goes, what it does for us, and so on. And the quantitative paper, so this is something that I hope to cover in the first lecture. And then these are the quantitative papers. Okay, so this first, this is the Breza, Isaacson, Parisi, and Zuber paper. And then the papers of Gross, Witten, and Wadia. And there's a paper of me in 1990, which generalizes some of these things. These are about matrices, and if you wish, these are like papers, quantitative papers on large N matrices or large N gluons. And these are papers on quarks, again at large N. These can be solved. Okay, so these are problems. So this was the proposal, okay, that at large N there is some simplification that happens for QCD, and which was not available otherwise, because, as I'm going to say soon, that there is no free perturbative parameter in massless QCD. So, so Tuft invented a rather subtle hidden parameter which nobody had thought of before, is to say that, okay, why not generalize SU3 to SUN, rather, in fact, most of the time I'll be talking about UN. And then he showed that 1 over N appears as a perturbation parameter. So, and so that leads to only a select, in the large N limit, it leads to a select subset of Feynman diagrams, which are called planar diagrams. And that's a very, very significant cutting down on the number of Feynman diagrams to compute. And but even so, of course, it remains a hard problem to compute all these, sum of all planar, all these dominant diagrams, which are called planar diagrams. By the way, I have got some Riemann surfaces with me, which will be used as a part of the lecture demonstration. So this is the torus, believe it or not. And this is a sphere. The sphere you can see, I think, from up here. So I'm going to use it a little bit. So these are two Riemann surfaces. So this is an experimental talk. Okay, all right. So let me start. So why large N? So shall I use the yellow chalk or the white chalk? Which one has been working better? White? Okay. All right. So why large N? So QCD, massless QCD, does not have a free, I'll explain what this means. With which with which we could do a perturbation theory. Perturbation expansion. Why is that so? That's because the theory is asymptotically free, and what appears like a coupling constant in which you could think of expanding in that coupling constant, it actually gets absorbed because of the running of the coupling constant into defining a mass scale of the theory. Okay, so let me explain slightly more. So let's say this is an endpoint function of quarks and gluons. And normally you would think of this as there being a coupling constant and there's a cutoff. If you wish, if you're sort of beholden to dimensional regularization, so then instead of lambda, you can think of this as mu. It's the same thing. Okay, so this turns out to be, so this G and lambda, they get transmuted to give a mass scale, which is called lambda QCD. I'll call it MQCD here because this is a mass scale really, to some power that depends on the power counting dimension of this Green's function. And this becomes no couplings, okay? Where MQCD is, it originates as follows, just a very brief thing. This itself could be a lecture, but it comes from the following fact that the QCD has this famous beta function with the negative sign, which implies asymptotic freedom. And the solution of this, okay, let me write just two steps here. So this, yeah, so the solution of this, so this beta G here is lambda dg d lambda. And the solution of this is the following, that it is e to the power minus 2 beta naught g square of lambda is a constant. And this constant is what is called the mass. Okay, so the solution of this equation is, believe me, that the fact that this is a constant. From the constancy of this, you can derive this. Okay, you can verify that. Of course, you derive this by doing perturbative QCD diagrams, etc., etc. So this is, of course, well known. The minus sign implies asymptotic freedom. And so this statement is true, as you see, that you could have said that, okay, let me do some perturbation theory in perturbation in G square, etc., but no such luck, is gone. Okay, so this is known. In all of these things that I'm saying, everything is said in a much more elegant and poetic way in Witten's paper. Okay, so you should certainly read that paper, this paper. Okay, all right. So now, however, what Toft found out is that there is a subtle perturbation parameter, as I said, okay, which is obtained by thinking of SU3 as a special case of SUN, okay, and I'm going to use the example of UN gauge theory, and so now, so large N QCD. So okay, so and I'm going to take n going to infinity, okay, to see what happens. Okay, and we'll see that major simplification does happen because of this stuff. I'll go very slowly. I apologize to the experts, in this part, because the large N counting that I'm going to do, that you should all get. Okay, and all right. So, large N QCD is defined by this. I'm not going to put numerical factors like 1/4 and so on, whatnot. It's a mean square, and I'm not going to be careful about signs either. Okay, where if mu is an n by n Hermitian matrix obtained from A mu, which is the n by n Hermitian matrix. So d mu that, this you all know, of course. And this is the gauge covariant derivative defined like this. That. Okay. So this theory has the following kinds of vertices and propagators. Okay, so this is the quark propagator, the gluon propagator. This is a 3 gluon vertex, the 4 gluon vertex, and there's a quark gluon vertex. Okay, and so these are all meant to be, the quarks are meant to be fundamentals of the, so I'm going to use the following notation. So although I have used psi here, following Witten's paper, I'm going to write a quark like this and an antiquark like this. Okay, and this I will run from 1 to n, and the gauge fields I'm going to write as Aij. Again, Ij will run from 1 to n. So this is the first index which I write upstairs, is the second index which I write downstairs. All right. So this is a Hermitian matrix, and this, as I said, is a fundamental quark. Okay, let's look at the partition function of this theory, connected vacuum diagrams. Okay, and so what does it mean? That there are no external legs, and you simply have to take a combination of these vertices, and you have to close them up by using propagators. Okay, so simplest example is, let's take this one. Let's take this. Okay, now I'm going to suppress even the mu nu indices because they are not going to play any role for me. Okay, so this has, okay, so where does the 4 gluon vertex comes from? So there's an a square here, g times a square, right? And so the square of this comes here. So you get g squared times a to the power 4, and there's a trace. Okay, so what does trace mean? Trace means the following. So Aij, Ajk, AKL, and ALI, right? And it comes with the g square. Okay, that's my thing. And I'm going to now insert this thing in the path integral, okay, and evaluate. Okay, in other words, I'm going to take expectation value of this. What does it mean? That means that, so I have some propagator here for the A, and this is the propagator for the Q. And now I can use the A propagator to contract them, such as this, let's say, and this, right? Now let me see what the gauge propagators are. So from here, okay, you will get some del A whole square kind of thing, but there's a trace. So the propagator has a structure. The kinetic energy has a structure which is a trace with derivatives. Okay, once I'll write like this, but I'm ignoring the Lorentz indices. So it has this kind of a structure. So basically, if I just exhibit the color indices, then it is like Aij, Aji. Okay, with, if you wish, some x, an integral, blah blah. Okay, I'm going to ignore this from now on. Okay, so this means that Aij, a KL propagator must be proportional to, so what does it say here? The kinetic term in the Lagrangian says that this must be equal to that and this must be equal to that, right? So there is a delta IL, and delta J, right? So let's use it here. Please do it as I do here. So I just use this. So this is the symbol for contraction, as everybody knows. This is that. So let me just use, in fact, this is what I'm supposed to get. So let me just write blindly this guy. So delta I J and sorry, delta. So from here I get delta IK, delta JJ, and from here I get delta KI and delta LL. Right? This is what it is. Now delta IJJ, what is the value of that? There's a sum. So all of these indices are sum. There's no hanging index at all. There's no hanging index at all. Okay. So what is there some suggestion? N. Very good. So that's N. How about this? N. And now these two guys together will give me delta Ki, so that's delta II. So that's N square times delta II, so that's another N. So that's G square N cube. Okay? Let me write that as G square N suggestively as G square N times N square. I will tell you why later on. Okay, so there is one such thing in which neighboring A's have been contracted. There's another such contraction, and you can do that exercise yourself. Please do. There's another contraction in which, so in terms of this, what I'm doing here is that the previous contraction was something like this, like that. Let me close by gluon propagators. And then there's, of course, another one in which I do this. So that would correspond to this and this one. Okay? And that will give rise to exactly the same kind of stuff, and you will get a factor of 2. So from these two contractions, which I have already shown, so this plus this gives rise to 2 G square N square. Okay? G square N cube, which I'm writing this way. Now comes the interesting one, in which I contract this with this one and this with this, in which this propagator should not intersect. So you should draw a little bridge going above this one, okay? Like this. Okay? So it requires a bridge. That's important. So remember this. And now let me do that one. So let me write this vertex once more. AKL, ALI. So what I'm doing is this, right? This contraction. Now let's see. So I get delta Ij from these two things. I get delta IL, and delta JK, right? Delta JK. That comes from this contraction. And from here, I get delta JL, and delta KL, delta LK. Okay? No such structure has appeared, delta JJ, delta LL, etc., etc. And now let's simplify this. So these two you can combine to get one delta KL, and this you can combine, which will become delta, sorry, excuse me, I'm making a mistake here. No, it's correct. Delta KL and, oh, so these two gives me delta ILJK, and these two gives me delta JL and delta LK. No, that's correct, it seems. Okay, so let me do it this way. These two together gives me delta JK, right? This one, right? JI, yeah, okay, good. That's what was confusing me. So now this should be delta KI, these two deltas together, and this would be delta IK, good. Delta KI, delta IK. So eventually there is just one delta II. So all indices, okay, because of these deltas have become just one index. So you get delta II. So therefore it's given by N. And of course the vertex factor, so G square N. So what you get eventually with all the three contractions here is that you get G square N times N square by 2 plus the G square N with no factor of N at all. Okay, so this is, okay, so now there is a certain interesting thing about how to understand these factors. So the topological understanding. So we are going towards some topological understanding of these expressions. Okay. So what Tuft suggested is that, and this is brilliant because you see that chasing all these Kronecker deltas is a pain. Okay. So instead of that, he said that for gluon propagators, let's use double lines because the gluon has two indices. Okay. So, and for quarks, let's use a single line. Okay. So this is how the gluon propagator, let's say there's some Aij sitting here, and I must put, as you know, there's some Aj sitting here, and let's use the convention of putting arrows on these double lines, okay, so that if the arrow, if the color is up here, then the outgoing arrow, let that use, let it carry I, and this should carry J. And you see here, the AJI means that J should go out and I should come in. Okay. So the appearance of the kinetic term says that, you know, the color lines, the indices are continuous. Okay, so this arrow is not breaking in the middle. So if it was like Aij going with Aij, then I runs like that, then I would have run like that. But that's not how it is. Okay, so the index lines are continuous. Okay, so that's the thing. Now, let's write this vertex. Let's write this vertex here. This is how the, you know, the Aij contracts with Aji only. If you wish, let me say it in another way. Suppose you do this, Aij with AKL. This 2-point contraction is what you want to, is it already clear? Okay, good. So in this case, what you would have done is to say, well, the K should go out. Or you could say even, okay, so I'm using this thing and L should come in. Okay. So in this, I has to be equal to L and J has to be equal to K. And that is indeed what the 2-point function is, wherever I wrote that, the 2-point function. That I has to be equal to L, that's what it is, and K has to be. So the 2-point function itself says that the color lines are continuous. The index lines are continuous. Okay, now I claim that this is how the 4-point function, the 4-point vertex, the gluon vertex looks like, okay? So just so that I don't make a mess of things, so I use convention like that, Aij. So Aij, remember, like this. So there are 4 A's in this, so they go out like that, and indeed, the color continuity of the color line says that this must be J going out now. And this is K, and then continuity says K should go out here now. L, something comes in, that's L, and then this, of course, this must be I going in, and this is how exactly it is. Okay, this is how exactly it is. You should check this. Now let's do the 2 contractions, the 3 contractions that we did earlier. So what do the contractions say? They say that this is how it has to be, okay? Now let's forget the fact that I have used I, J, K, L, etc. They will all take care of themselves. I just draw the arrows, okay? And this guy. So the contraction rule is that as long as the arrows are continuous, okay, I'm done. I don't have to check anything at all, okay? And now let me count the number of index loops, okay? So there are some, so let us say if I call this I and this is J, this must be, oh, excuse me, I already made a mistake here, this way. Oh. Oh. Ah, no, so I was doing it right actually. Okay, all right. So it is like that, it is like this, and then it is like that. Okay, so how many indexed loops are there? There's one color running here and coming back. So that's one, okay? There's one color going like this and coming back, that's another one. So that's 2. And then there's one color running all the way around like that, blah, blah, etc. So this is the one that eventually become delta AI, delta II. Okay, so that's the outer loop. So therefore, there are 3 index loops, 3 index loops. And of course, the index is free to take any value that it wishes, just like momentum on a loop can be anything, index can be anything. So therefore, there must be 3 factors of n. So that's n cube. Okay. So you just draw double line things, contract them. Okay. You can even forget about, eventually you can forget about the arrows. If you have done it enough, then it's n cube. And of course, the vertex factor was g square. So you get g square n cube. Okay. So just these crosses and contract them using double line propagators, and you're done. So g square n cube. Similarly, if you do it this way, there'll be, like this and like this one, like that. That would be g square n cube again. So it would be, these two contractions will give you 2g square n cube. And this one here, eventually, so that's one. That is like this. And another one is going above like this. And let's count how many index loops there are. Let's start chasing the index line. So let's start from here. Like that. Once in your life, you should do this. Okay, I go like that. I'm going down. There you are. Just one. Okay. So therefore, only one index loop. You should really, chase this index line once. Okay. So therefore, one index loop. Of course, it had to be because we derived it. Okay. So therefore, it's n, and of course, there is a g square. Okay. So therefore, double line diagrams, okay, they tell you immediately without doing all this Kronecker delta gymnastics that how they go. However, Tuft went further. He said that let's attach a little surface to each of these index loops. Okay, so for example, okay, I have made a little mess here. Let's take this contraction. Now let's imagine drawing this on a piece of paper, okay, like the blackboard. And let's fill out all these index loops by some color. So this index loop has yellow. This index loop has green. And the outer index loop is drawn on a piece of paper. So you should fill it up on the outside. Okay. So let's say, in order to minimize the amount of paper that you waste, you just fill out so you get 3 colored patches with some lines running. Okay. So this is what he said, is that you get some two-dimensional structure, and when you have more and more such things, okay, basically you get some structure like this. Colored patches. Oh, by the way, I forgot. So instead of a plane, you could think of identifying the boundary of the plane to a point. Then it becomes a sphere. Okay. So this is some diagram. Okay. This set of contractions, that I have done, it can be drawn on a paper, plain sheet of paper, or it can be drawn on a sphere. Okay. So on this sphere, you can imagine that there's a cross somewhere, like this double line cross, and then you just do this stuff. Okay, so I cannot do the demonstration. You should do it yourself. But it's like this. So it would be, this sphere would be filled with 3 colors in this case. Okay. Okay, good. How about this guy? Okay, this you cannot draw. This you cannot draw on a piece of paper because there's a little bridge here. Okay, so you need a paper with a bridge. That's a paper with a handle. So that's this. Okay, so you should draw this, the 4-point function here. And then one should go under, the other one should go over the handle. Okay, so that's it. This is a sphere with a handle. If you, this is a fat cup, so you should. This is all a single surface. So this is really a torus. But if you're more comfortable, then close this thing. Okay, then it's really topologically a sphere with a handle. So this is what he said, that you need one handle here, and you need no handles here. So more generally, this is of a form. So and then there are coefficients, and then there are coefficients depending on the G square n quantity. Okay, so he said more generally, it will be of the form where h is the number of handles, is an integer. Okay, so if you take arbitrary gluon diagrams, okay, and let's say the vacuum diagrams with no external legs, then they would be of this form. Okay, in this example, what have we got? For h equal to 0, we got that a0 of g square n is 2 times g square n, and for h equal to 1, a1 of g square n is equal to g square n. So this combination of g square n, so now you see that already it says that h equal to 0 dominates. Okay, so this is what is called the dominance of planar diagrams. Okay, and I'm going to prove this. Okay, this is what. So these two contractions, these two different ways of contracting, they fall into this pattern. But I need to of course convince you that this is what really happens. Okay, so yeah, h is the number of handles. So h is the number of handles. Here I didn't need any handle at all. It's this. That's it. Right? But this cup is a sphere with a handle like this. I need one handle here. Okay, so you agree that the result that I got, namely 2G here, this one is of that form, right? So he said the following. This is Tufts' work. Let's take n going to infinity and g square going to 0, so that g square n equal to lambda is held fixed. Then this quantity looks like 2 lambda n square plus lambda, right? And this dominates quite clearly. So this is the planar dominance, the dominance of planar diagrams. And let's prove this, okay? Okay, never mind. It's important to go through this slowly. Okay, a more general proof. So I'm going to prove this now to you, okay? So let's say that consider a diagram, This is, I'm still doing only gluons. I'll include quarks later on with V3 vertices, V3 3 gluon vertices. So the number of 3 gluon vertices in that graph will be V3, and V4 4 gluon vertices. Okay? Yes. No. So this is the function a naught of g square n. So this is what it is. So let me not write this G square n here. Now that we know that G square n is supposed to be called lambda, let us look at this diagram. Let us look at this expression. Right? This expression is like A0 of lambda times n square plus A1 of lambda. Right? According to that thing. Is it clear? Once more. H equal to 0 means this n square. And h equal to 1 means n to the power 0. So that's 1. Right? So this guy, okay, in this instance, will be like, right? It's just A0 of lambda times n square plus A1 of lambda, where I can read off A0 of lambda to be 2 lambda and A1 of lambda to be lambda. Right? Is that clear now? So let me not write things in a complicated way. So it's just lambda, and 2 lambda, and this is just lambda. Right? That's what it is. Okay, good. So let's give one example, like V3 equal to 2 and V4 equal to 1. So two cubic vertices, and so two cubic vertices. Two cubic vertices and one quartic vertex. Okay, before joining, so this is what I have. I have two cubic vertices, V3 equal to 2, and one quartic vertex. Okay, so let's join up now, like this, like this, like this, right? So let's compute now the number of propagators. So this is the clever trick of Toft. So he says, let's compute the number of half propagators. Okay, so let's put a dot in the middle of each of these propagators. Dot. There's one propagator here. It's a dot. And then there's a. Okay. So there were 5 propagators, and therefore there are 5, 1, 2, 3, 4, 5 dots, right? The number of half propagators is twice the number of propagators. Look at the number of half propagators, meaning that count this one and this one separately. Okay. So what is the number of half propagators here? Can somebody say? So if the number of propagators was 5, the number of half propagators will be 10, right? 10. So 10. And now each half propagator is stuck to a particular vertex only, right? So therefore, therefore every cubic vertex has 3 half propagators to it. Is that clear? This is the cubic vertex. It carries 3 half propagators, this one, and this one. This is the quartic vertex. So it has 1, 2, 3, 4. 4 half propagators. So therefore, I get, so more generally, I get the number of half propagators, which is 2p. The p is the number of propagators. That would be 3 V3 plus 4 V4. Very clever. This is what Toft did. Okay. Now let's compute this kind of a diagram. So the propagators don't have any weight at all. This is the convention in which we are doing it, that there is no factor of n or factor of coupling, anything like that here. Okay, so propagators don't give anything. The vertices, so each vertex each cubic vertex contributes a factor of g. So g times v3, and each quartic vertex contributes a factor of g squared. Okay, and the number of index loops, let us say, is f. Why do I call it f? Because they are like the faces. Okay, there are just these many faces here, 1, 2, 3. Okay, so the number of index loops, let me call that F. And now comes a real fun thing. Okay, so this is the value of the diagram. Let's write it. Let's count the number of 4. 2v4 plus v3, okay, n to the power f. I have not done anything, I have rewritten the same thing. And now, let me write this as one further step. I'll write it in terms of g square with v3 by 2 here, right? This is the same thing as this, v4, g square to the power v4 plus v3 by 2. Good. Now let me bring in a factor of n here. So g square n times v3 by 2 plus v4. So I have borrowed that much, so I must subtract. So n to the power f minus good. N to the power f minus whatever I have borrowed, which is v3 by 2 minus v4. Okay. Now, Tuft used the Euler's formula which says that the Euler character of a surface, the spheres with handles, they're examples of what we call Riemann surfaces. So for a Riemann surface, where the Euler character you can define by this is the surface, and this is square root g times r. This is a topological invariant. On one hand, it is given by 2 minus 2h. On the other hand, when you use this kind of a what is called simplicial decomposition of the Riemann surface, have the scaffoldings and count the number of vertices, edges, and faces. Okay. So this is given by face minus edge plus vertex. So the edges are the propagators, right? And the vertices are, so vertices here, in this case, the total number of vertices is the number of cubic vertices plus the number of quartic vertices. So that's that. And the propagator is given by here. So that's 3 by 2 v3 plus 2v4. Okay, so let's subtract these things here. So I get f minus 3 by 2 v3 plus 2v4 plus v3 plus v4, right? So then I get, what do I get? F minus v3 by 2 and minus v4. Surprise, surprise. So this object is just the Euler character. Okay? And the Euler character, as I said, is 2 minus 2h. Okay? So therefore, it becomes a topological expansion. Expansion in topology where the spherical topology or the planar topology, plane is being thought of as compactified at infinity to make it a sphere in which the dominance of the sphere. So this is another way of saying that planar thing, planar dominance. So since I'm going painfully slow, let me just claim that if you look at string theory worldsheet diagrams of various topologies, you get exactly this. You get exactly this expansion with n being, so this is like a string theory. In fact, Toft had two motivations. One was that he was trying to describe QCD. He said, okay, there are no free parameters. What do I do? So then he invented n. Okay. So you see, okay, so it's the power series is in 1 over n square. Is that clear? It's 1 over n square. Where is it? Here. So every increment of h by 1 gives you suppression by 1 over n square. So pure glue diagrams have suppression. It's a power series in 1 over n square. We'll bring in quarks now. So anyway, so the other for him the other motivation was that the mesons were like strings of glue connecting a quark and then anti-quark. So those days, people thought that QCD must be described by string theory, okay? And he must have been very happy to see that the topological expansion came out, because it's the same topological expansion that comes in string theory. Like if you have closed string diagrams, then the vacuum diagram from closed string starts and ends. Okay, that's a sphere. And then, a closed string, la, 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 like that, it can split. And it ends in vacuum. So this is a torus, and so on and so forth. And indeed, this guy, has, because of the worldsheet reasons, which I'm not going to get into, 1 over G string square, okay? And every handle gives you a factor of, additional factor of G string square, okay, upstairs. So, this expansion, therefore, exactly matches that expansion with the identification of 1 over G string to n. Okay, and this was, of course, quantified by Maldacena in what is called the ADS-CFT correspondence. That would be another thing that I will express another time. So let's include quarks now. Let's see what happens with quarks.
Sir?
Yeah.
With this formula, it seems that a h of lambda will also depend on n, while it should not, right? Because that formula...
No, it's not depending on n. Once I write g square n in terms of g square n in terms of lambda.
But as we go higher in the diagram, the vertices will change v3, v4, right? And
yeah,
that formula, n to the power f, g to the power v3 and g...
No, this is absolutely general. This is for any v3, and this is just an example. For any v3 and any v4, these statements are all true. That the propagator is given by, 2p equal to blah, and the diagram is given by this. And I just, showed you that this diagram, in terms of just keeping track of G and N becomes...
I'm saying that as the handle will change, the vertices will also change, right? The vertice, number of vertices will change. V3 may be, so in this diagram...
yeah. Of course.
And that will change. And this is the factor of a h of lambda that is coming in the series.
Correct. So when you take another diagram...
Yeah, it will have different vertex.
It will have different V3, exactly. So eventually here, this guy, okay, yeah, okay. Are you worried about the V3, V4 dependencies of this one?
Yeah, because
then... yeah, certainly. It will be a power series for any given fixed number of handles, okay, this is going to be a certain power series. H of lambda will be lambda plus lambda square plus lambda cube, etc., etc. Yeah. So that's a hard thing to compute. So this AH of lambda, okay, they are like the sum of planar diagrams with arbitrary number of V3 and V4, okay, in the pure gluon theory. Including the quark, it makes the job even harder. So let me just say, with quarks, what happens? So that's true. It's not independence that, and no additional independence that comes. But these things, of course, I mean, you could go to the example that we already had. Let's see. So here, the V3 was 0, right? It's a V4. So V4 was 1. Right. So it's just G square N. Okay. I have not put in here combinatoric factors, how many contractions are possible. Those are those integers 2 and 1 which appeared here, right? It's a 2 because there are 2 contractions, blah, blah, etc., etc. So that's what it is. This is very general. Okay. Right. Introduce quarks now. So what happens is that this formula gets changed to, I'm just writing down the general formula. If I can ever find it. Yeah, here it is. So now, in addition to drawing handles on a sphere, you can draw cuts. You can draw boundaries. Okay. So if you draw on the sphere a boundary like this, take it out, then that becomes a sphere with a hole. It's not a handle, it's a hole. Okay. I have cut out one disk from here. And topologically, the remaining thing is just a disk. Okay. So okay, I had no idea that I'll take this long. Okay, good. AHC. What are the timing things? So I should take only 45 minutes. Is that right? Or no, so let me take, because this is I wanted to finish the sort of qualitative part as, so the claim is that with quarks, the diagrams would now have a sum over the number of handles and the number of holes. Okay, I cannot use H anymore because H means handles for me, so I'm using C for cuts. Okay, cuts meaning how many disks are cut out. And here now again the formula. So this is these coefficients are functions of lambda only, and this is n to the power chi again. But now I have to use a modification of Euler's formula for Riemann surfaces with boundaries. Okay, so for Riemann surface with boundaries, it's given by 2 minus 2h minus c. Every disk that is cut out, okay, that will correspond to one subtraction like that. Okay, and let me just give you one example. Let me give examples involving some current to the a quark bilinear of some form like this. Okay, J of x. As usual, I'm going to ignore the space-time indices and even flavor indices and so on and so forth. Okay, so I'm going to ignore that. And so and I'm going to compute Jx, Jy. So it should look like it's a quark bilinear. So Jx looks like this, and Jy also looks like that. Now I have to join them by using quark propagators, gluon propagators, and whatnot. Okay. So if I just join them by a quark propagator like this, so how many index loops are there? 1. So it's just this. Ignore the crosses. It doesn't matter. The color is continuous across these crosses. Okay. So therefore this is n. How does it match with this thing? Because now you do the same thing. Every index loop has to be filled out either inside or outside, it doesn't matter, okay, whatever is available to you. Here, I have put that in, so therefore it's a disk, right? This is a topology of a disk, and for a disk, let's apply this formula. What is the thing of a disk? No handles here, but there's one cut. A disk, remember, as I had just explained, a disk is like one loop cut out of a sphere. So the number of holes, or hole, the number of holes is 1. So h is 0, number of holes is 1. So therefore, chi is equal to 2 minus 1 is 1. And indeed, is n to the power chi. Okay, so it's like that. Now you can put in as many number of, so let's say you put in gluon diagrams, etc., with complicated stuff, and it will continue to remain as long as you are not drawing bridges, it will continue to be n, because let's say if you have some thing like that, thing like this, and you should draw them really carefully to like that, la 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 la, and fill in all the index loops with different colors. But eventually, you are just triangulating a disk. Okay, the topology remains a disk, that of a disk. Okay, on the other hand, if you do this one, let us say you have something like this, right? So how many index loops have you got here? 2, right? Good. Where does the 2 come from? Again, this is a surface from which, if you think of a sphere, the outside is the thing that has been cut out. Okay? And there's one hole that has been cut out. So the disk was already a sphere with a hole. Okay? Now from the disk, a hole has been cut out. So there are 2 holes compared to the sphere. Okay? So then the chi, so here, no handles still, and the number of holes is 2. So therefore, it's 2 minus 2. That is, oh, sorry. I should not say this is the end. Excuse me. I have not done anything here. So Toft says that it must be n to the power chi. So that's n to the power 0. So that's 1. Let's see whether diagrammatically is actually true or not. So there's a G here, there's a G here, there's a G here, and there's a G here. There's a G here, right? So that's G to the power 4. And there are 2 index loops. So that's n square. So that's just lambda square. Indeed, there is no factor of n hanging around. Okay, so that's just lambda square. Okay, so I can do this more generally, a proof like that, but I don't have time for that. Okay, so this already tells us some interesting things, which okay, one thing that it says, so now I'm switching from Toft's paper to Wheaton's paper. One thing that it says here is that internal quark lines are suppressed. Okay, internal quark lines are suppressed. So every time you draw an internal quark line, okay, is down by 1 over n. Now this is Wheaton's observation. So he says that if you start with some QQ bar state and draw some intermediate cuts like this, QQ bar here is still QQ bar. Okay, it's propagating as a QQ bar. Now what's happening here? What's happening here is that there's one QQ bar which has split into 2 QQ bar states. There's a QQ bar here, there's a QQ bar here. I can do the indexology here. You can do this yourself with gluons and stuff. But one meson splitting into two mesons, okay, is suppressed. Okay, so mesons are free in the large n limit, in the n going to infinity limit. Okay, so this also says that this exotic mesons like the QQ bar bound states. Okay, meson bound states which are supposed to be there in the large n limit, in the n going to infinity limit, they just split into two free mesons. Okay, so meson bound states, these so-called exotics, okay, they don't appear in the n going to infinity limit. And Witten says that that is borne out by phenomenology because such exotics are suppressed. Okay, so here, of course, the experts can verify or disprove me, but this is what Witten had said back in 1978. Of course, such exotics have been found, but I presume that the QCD is no. What Witten says is that even for SU3, okay, so this part is about how good is this. Okay, so I'm jumping because I'm going very slow. How good is this large n thing for real world phenomenology? So he says that apparently the production of meson bound states are suppressed. Okay, is that still true? Okay, good. So that is what it is, and the suppression of the internal quark lines also says that it's not the quark C that contributes to this state. Okay, but gluon C, of course, that does contribute. So the suppression of the quark C, just this simple fact that there is an n to the power minus C that appears here, which says that for every internal quark line, okay, and this is also seen in the, So the point here is the following, that large n, you cannot use large n, as Tuhin pointed out, for n equal to 3 for quantitative purposes, but many qualitative things can be sort of figured out from there. There's another, there are many lovely examples that Witten gives, but let me show you, one example, and after that I'll close this one. Oh, I'm already over 1 hour. I'm already over 1 hour, isn't it?
Yeah. You will have a break and then you come back, right? So I'm deducting the time.
All right. So yeah, maybe I'll come back and do that part because I need to go over that slightly slowly. This just to say that the JJ. So what I'm going to do next is to show that these J's create one meson states. So in other words, JJ has spectral decomposition like this is what is there in Witten. So this is JP. So I have to bring in a little bit of space-time here. Where this is what will say that he in fact deduces the existence of this, in fact, infinite family of meson states by looking at the possible spectral decomposition of the JJ, current correlator. And from there, all these facts that the triple meson vertex goes as, is suppressed. In fact, it goes as 1 upon square root of n. The quartic meson vertex goes as 1 upon n, etc., etc. All that can be deduced. I will come back to that because I don't really want to hurry it up too much. Okay, all right. So we break now, and unless there are some absolutely pressing questions from somebody. How is that proved? That's a bit detailed, but it's a topological, is there in math books. Riemann surfaces with boundaries, yeah. It's not too difficult, but not a one-line proof. I mean, the proof that I know is not a one-line proof, but somebody might, maybe ChatGPT might know. Yes. Basically, the point is that the quark lines, okay, they are a single index line, not a double line. As a result, when you have a quark line instead of a gluon line, you have a suppression of 1/n. That's the basic point, that there are n quarks and n square gluons. Yeah. So maybe that's a simple way of saying it. All right. So we'll meet whenever the boss says.